Okay, we're back. This is AP Physics 1, check-in number 7. This one has to do with rotational motion. Has been the case. If you haven't looked at them, go ahead and read the question, pause, and see if you can answer it, and then we'll go back through. So, the first question is, if two children ride a carousel, one on the inner rail, one on the outer rail. So that's the scenario. Which child has the greater angular speed? And I think you would see that has to be the same as you go. It wouldn't matter which part of the circle you were on. As that thing rotated anywhere on there, you're going to have the same sweep through the same angle. Therefore, if angular speed is the angle over the time, it's got to be the same for both. But that is not the case for B when it says which one has the greater linear speed. Well, linear speed is r times omega. So, and that makes sense because it has something to do with how far out you are along the way. Person on the inner rail here versus the outer rail, this person on the out has to go a greater distance in the same amount of time. Therefore, the answer to that is the greater speed is going to be the one on the outer rail. Okay. Same kind of question, but it says, as the carousel comes to a stop, which child has the greater angular acceleration? Well, angular acceleration is the change in angular velocity in a given amount of time. But at any given point, the angular velocity is the same for the inner and the outer. So I'm going to again say that even though it's changing, it's the same change for both the inner and the outer rail. But would that be true about the linear acceleration? Well, the linear acceleration is equal to r times the angular acceleration. But as you go out to a greater r, even though you have the same angular acceleration, you're going to have a greater linear acceleration. So we're going to again say on the outer rail, you're going to have the greater linear speed and the greater linear acceleration. But the angular speeds and angular accelerations are going to be the same. Okay? So that's that question. The next question is more of a rotational kinematics. It says a disk initially rotating at 13 radians per second slows down at a constant rate of 2 radians per second squared. What is the angular displacement in a 5-second period? Okay. So the initial speed is 13 radians per second. The angular acceleration is 2 radians per second squared. And the time is 5 seconds. So we're just writing all the given information. And what we're trying to find is the angular displacement. I think I'm going to use the equation. Angular displacement is the initial angular speed times time plus 1/2 angular acceleration times time squared. In this case, that's going to be 13 radians per second times 5 seconds. And then this is going to be 1/2 2 radians per second squared. And then we have to 5 seconds quantity squared. Okay, 13 by 5, I think that's 65 radians. And this is 1/2, those cancel, and 2, 5 squared is 25. Wouldn't it be correct to say then your total angular displacement in radians is 90 radians? Sounds pretty reasonable. Okay, on to the next question. You now have a situation here where you have a mass connected to a pulley by a string, but in case now the pulley itself has more mass. Usually we've done at-width machine problems and problems with pulleys with massless pulleys. Now we're going to try to figure out how do we handle a situation if the pulley has mass. Okay? So in this case, we're going to determine an equation for the angular acceleration and the tension in the cable. Excuse me, the linear acceleration of the pulley and the tension in the cable. Okay. Well, we go by the angular acceleration because we know that that's equal to the net torque over the moment of inertia. We're going to consider the pulley to be a disk. So let's see how we can put this in. If we look at the free body diagrams of the situation, for one, I think it's going to have a force due to gravity acting down. It'll have a tension force up. At this point here, that's that same tension force, but that tension force is what's going to supply the torque. So when we say, what is the net torque? The torque is going to be that tension force times the lever arm, which is the radius. And if we go ahead and use that idea that this is a disk, that would be 1/2 m. In this case, it's the mass of the pulley, which I have labeled as 2, and then this would be r squared. One of the r's will cancel, and that's going to give me the tension over 1/2 m times r. But we could also say that that's equal to a over r, because of the fact that r times alpha equals a. So if we want to know the linear acceleration, that's going to also cancel another r out. So the actual linear acceleration is just the tension over 1/2 the mass of the pulley, which we have labeled as 2. So that's one thing that we've gotten. Okay. The second thing would be if we took the other free body diagram and tried to make some sense of that equation, and that would be A equals F net over M, but that's going to be the force due to gravity on the object that's hanging minus the tension force all over the mass of that object. So if you did that, that's like M1 times G minus Ft all over M1. And the idea is that now we have two equations and two unknowns, so we could actually put them together and see if we can do some solving of that. And maybe that would be worthwhile to take a little bit of time and see what we could do with that. If we do that, let's see what we can do. So we have those two equations. A is Ft over 1/2 M2, and A is M1G minus Ft all over M1. So if you wanted to, you could put the two pieces together, and we could just say that these two things were equal. So Ft, I guess if I just automatically put them equal, then wouldn't that be Ft times M1 cross multiply, and then this would be 1/2 M2 times M1G minus Ft. And so you'd have to do a little bit of cancellation and moving things around, but if I bring this to the other side and do some factorization, move 1/2 M Ft to the other side, this is going to be Ft times M1 plus 1/2 M2, and on the other side it's going to be 1/2 M1 M2 times G. So Ft would be M1 M2 G all over that factored part, something like that. So that just gives you an idea of how you could put those two pieces together to find out what the tension force in that cable would be. Okay, so that's one problem right there. We're going to end up with one ranking task question and see if we can get through that fairly quickly. And it says, arrows here represent forces of the same magnitude acting on each object. So you have one here, two here, two here, two here, two here. We're labeling them A, B, C, D, and E. And they want to know is rank them in terms of the acceleration. So this is basically saying rank them in terms of the force. Which has the greatest force? This has one force. These two have in different directions. But don't they cancel? So if you rank them, I think that's going to be one of the least. These two are both in the same direction up. So that I think that's going to be the greatest. And then D has part one way, part the other. So if I'm going to rank it, I think I'm going to say C is the greatest force, therefore giving the greatest acceleration. D and E appear to have the same forces when you add them together, one up, one to the side. Then A will be the next because it has one force by itself. And then B, because it's got two forces canceling, would have a linear acceleration equal to 0. And then the last thing would be to rank in terms of the alpha. Now we're going to look at the torque. Notice that this produces a torque in the clockwise direction. So would this. So would B in the effect. But C, the one on the left produces a counter or a clockwise torque, but the one on the right produces a counterclockwise torque. So some of these are actually going to give you 0 acceleration, angular acceleration. See if you agree with me. I'm going to say B and E are both going to give you torques that are going to give you twice as much torque in the clockwise direction. Then I'm going to rank A next, and then I'm going to rank C and D as 0 because they're going to produce no net torque on the object because the two forces are producing torques in opposite directions. So C and D are going to cancel. Okay. Go back through and see if that makes sense, and then email me if you have any questions. Otherwise, I think we're good. Hope you have a good one. Stay safe. Talk to you later.